So this is a bit of an experimental talk in the sense that not that I'm doing anything amazingly weird in it, but it's the first time I'm giving it, which is so I'm happy to get feedback at the end about like what came through clearly, what didn't, and this touches on a lot of theory on how these problems are challenging to solve, perhaps even more than what we're actually fundamentally doing at Pantheon to address them, even though I will include kind of our own answers to these problems as part of this. In a possibly over-clever language of the agenda, like the three ways that I'm going to look at this topic is in terms of Tetris, Tupperware, and trade-offs. Tetris is the idea of some of the most basic theory around fitting together things from a bin packing perspective and why mapping requirements and needs for things like handling web requests to resources is challenging. Tupperware is named somewhat after the internal container implementation at Meta. Not that that has any relationship to the infrastructure at Pantheon, but it had started with T. And I got this. That fun little story. I was talking to some of the folks from there about a year ago when Tupperware was about to declare bankruptcy, and there have been some internal discussions there on like, should we just buy the company so we can actually call the system Tupperware, because they're not actually allowed to publicly talk about that, like because the brand, they don't want to deal with the trademark thing, but it would be quite funny if like they ultimately got bought up and then used to name a container system on Linux. And then trade-offs is the idea of like balancing the different needs in these systems, like having built up over those two previous categories, how it's impossible to solve this problem perfectly or realistically, not reasonable to solve it perfectly, how the different trade-offs balance and what options Pantheon has chosen for some of the path forward and what kind of data we're seeing out of that. So Tetris, a tetronymic tour of tessellations. It's not even really tessellations, but the so I mean I love Tetris as a concept because it actually is super easy for people to relate to, but it actually exposes a bunch of interesting computer science concepts. The first one, like I like to talk about, is like how if you have a narrow enough board on your Tetris game, it's going to be basically impossible to win. Like this, if you pull out a Game Boy or a Switch or like whatever you're playing Tetris on, or whatever like generation you're at on that, you would be flabbergasted if this was actually a level you were expected to play, because even if you played this game perfectly, you would very rapidly lose because there's not actually enough fungibility of where those pieces can go. I don't have any animations in here, but like just imagine the parts at the top kind of dropping, coming in. This is intended to be a bit of a metaphor for requests coming into an infrastructure. At Pantheon, we have just under about 1% of page views on the internet coming into our edge on any given day. And we have to route those to the containers that can actually successfully handle those requests. Those containers have to have the right code deployed for a customer's Drupal site. It has to have those resources be hot enough, and it has to have enough resources to handle the request. So if every request coming in is a Tetris piece, at the edge and at the cloud origin, we have to figure out where to drop that piece. So we can't do this. We can't just have a narrow set of resources, because it's quite obvious how as soon as you have the wrong combination of requests come in, you lose the game. And in this metaphor, losing the game is failing to have enough resources to correctly handle a request. You can also switch it up to the other direction, where if you have a board that is ridiculously wide, no one would ever be impressed with you actually playing Tetris well on this board. You could get to a level like 1,000, and it would be like, what does that actually show me? Because like this is an easy board. And the reason why this is easy is it's ultra wide. You have so much fungibility around where you can drop those pieces. This makes the game easy to play, but in the world of kind of cloud computing resources and the metaphor here, making this wider costs money, in the sense that every block of additional resources for where you can drop those requests is a cost. And the reason why you should care about the cost to an organization like, say, Pantheon is we also have to price our products according to the cost that we have. So the cheaper we can do things, the better we can price our products for customers, or the more generous we can be with certain resources. Like, part of why we're able to have things like multi-dev on Pantheon is because we've been able to get our resources to be really efficient for certain things. And that means spinning up these additional environments is not actually that heavy weight. But there are other ways to look at this problem other than just the width of the board. Another way is, like, you can constrain the pieces. Also, no one would be impressed with you winning this Tetris game. If your pieces are standardized enough, it doesn't really matter that much how wide your board is. You will be able to continue allocating them, building up the full rows, having them disappear, and you could basically play this forever. This is analogous to constraining the complexity or nature of a request before it gets allocated to a particular set of resources, where if we know that a request is lightweight or has certain properties or heuristics, like the user might not be logged in, then we can distribute it. You can turn this into a way to handle the requests in a sort of serverless system, where if the request matches constraining criteria, like say it's an anonymous request, it's likely to be reasonably lightweight, it's possible to possibly send it to a resource pool that is kind of tailored to handling that type of request. And this can handle a lot of requests with this type dropping in here without running into problems because they've been constrained. And then you can have a wider board on the right for irregular requests, like going to admin URLs, having active sessions. And part of why this is also quite interesting from a cloud infrastructure perspective, and this is where the metaphor starts breaking down, and why I'm about to abandon it for the rest of the presentation, is that in the world of serverless and scale to zero, the width of your Tetris board is actually kind of dynamic. And there is a time or cost basis for widening it, which kind of gets into, like, if you were dealing with AWS like 10 years ago, you would often have to warm things for auto scaling, where, like, before the morning traffic would come in for your website or your e-commerce system, or if you were having a big sale, you would fire some traffic at the system to kind of expand the board so that when all the pieces come dropping in, you actually have a place to place them. So it doesn't completely fall apart, but, like, it starts getting a little rough. So I'm going to switch to a more direct kind of look at these. But before I do that, like, if any of you have a computer science background, this problem is NP hard. The NP hard in the sense of how much actual time would it take for a system to perfectly allocate the mapping between incoming requests and resources. So we don't try to do this. I'm not going to get into a bunch of complexity theory here, but the only point I'm trying to make is there's no perfect solution to this. Every solution for this comes with trade-offs, constraints, and it's really an engineering problem at that point, because we can't solve it perfectly, so we just need to solve it well. So we don't map these things to Tetris boards, really. We map them to containers in the cloud. And containers in the cloud have different sets of resources in them. It's almost like we're mapping requests to actually a set of Tetris boards, where as we allocate them to a container, that container then has to deal with the falling piece and placing it and handling the request. This is intended to kind of provide the way that requests may come in for a particular website. This magenta on here. The stacking represents the individual requests. You can see that the requests come in at different points in time. They last slightly different durations, and we can't necessarily predict what we will see in the future just based on the left side. Like, at this point, we don't know what is going to be arriving. But the staggering on here is somewhat representative of someone loading a web page, which often loads sometimes up to hundreds of resources off the server. So this is a kind of very abbreviated version of that, where if you assume that this was the HTML, this was maybe the CSS, this is JavaScript, and this is like one other file, like an image file for a super simple web page, that's how it might happen, because the web browser actually often needs a lot of the data here to make the subsequent requests. There are different ways to deploy infrastructure to handle these requests. We have a spectrum between how the fixed cost on that infrastructure is for each unit of resources versus how flexible it is. In the sense that the most static version of resources is bare metal. And if you have a really predictable workload for systems, like if you're Dropbox and you're storing files, it actually sometimes makes sense to go back to bare metal or focus on that. Because bare metal per unit of resources is by far the cheapest. Like every gigabyte of memory you have on it, every gigahertz on the CPU, every core in the CPU is the cheapest of all of these options. But like, if you're talking to Rackspace about this stuff, you're talking about like a 1 to 3 year contract for a given set of hardware for traditional racked stuff. So a lot of people don't use this because the flexibility is too low and the savings aren't worth that compromise on flexibility. So we kind of have been moving down on this with a lot of infrastructure. Virtual machines can be acquired dynamically in the sense that you can usually get them fired up within some number of minutes. You only pay for them when they're running. They're often billed using, say, a second or minute level resolution. And they provide some more flexibility, but I mentioned they usually take minutes to come online. That's not actually fast enough to dynamically respond to the needs of traffic on a site. So you still need to deploy these sufficiently to handle at least the traffic spikes you expect to have within the next 15 minutes or so. And that requires a lot of forward-looking estimation, and it's actually also just a giant pain to do. As you get into container orchestration on systems like Kubernetes and serverless infrastructure, you start having start times that are so fast that it starts to become more viable to actually have those resources come online as they're needed rather than in anticipation of that need. But let's step through these and see how they actually map to the resource demands of these requests. Anyone who's taken calculus, this is almost like doing an integral over it, in the sense of we need the area, we're measuring the cost that we have for this infrastructure is the area under the curve, and the requests need to fit under that curve. And in this case, the curve here is the yellow area, where one option I have, if I'm, say, contracting with Rackspace, and I need to be in a 3-year contract over these resources, and it takes phone calls and DocuSign to get more, I need to deploy a lot. They might be cheap per unit, every gigabyte of memory and core, but I need to actually be able to handle not even the next 15 minutes, but probably the next few weeks of traffic at a minimum. And more likely, given the way these contracts work, you generally have to set up the infrastructure to handle your 99.95% case of the overall traffic. So there's a lot of yellow area on here that isn't being used for this workload. And in fact, if you look at the average utilization of virtual machines across AWS, I believe it's under 10% of their CPU is used on average. It's really not very efficient. This only makes sense if you have a super predictable workload or you're doing batch workloads, because otherwise the unit of each infrastructure, every level on this yellow is fairly cheap, but you have to have so much of it that it doesn't actually make sense. Very few people deploy an infrastructure for brand new projects this way. You can also have a classical scaling scenario around firing up containers with autoscalers with tools like Ingress and Kubernetes. These are where you are starting to allocate resources in anticipation of the need, where in this case, every time we have any requests going to a container, in this case, these are container level resources that can handle 2 requests at a time. every time you have a request come into a container, we're starting another container as a spare, because this anticipates a longer startup time, where even if you're using kube and ingress, the time to actually start a brand new container often takes a bit longer than you would want to wait for a new request coming in. So this is a lot tighter. We're paying more for these resources than we would with the previous example, but these resources are much more tightly tuned to the need here. But we also have a lot of waste still. We have this entire container allocated up there at the top in anticipation of a fifth request coming in that never arrives. So in this case, depending on the number of requests per container, we actually have 50% more resources deployed for most of this time than we actually need to satisfy this. And it's all because we're afraid of throwing a new request at a cold starting container that is able to actually respond dynamically. This is the model we're working on moving toward at Pantheon in conjunction with Google's Cloud Run infrastructure, where rather than starting up resources days before, hours before, or minutes before they're needed, we want to start them as soon as they are needed. It's called a cold start in the world of containers, and it creates a really interesting set of optimization problems because whenever you start up a container brand new, we have to have that able to serve a request fast enough. Now, the normal talk I give at this camp, which I considered like pulling some of the slides from, but ultimately didn't, is like Life on the Edge, and it's basically talking about the idea of what performance you need for a website to hit in terms of the kind of meaningful first paint that the site has in order to have a satisfying psychological experience for visitors. But I only really wanted one figure from that entire talk, which is you need a site to load in about 2.4 seconds. It needs to paint on the screen. If you take longer than that, users become impatient and frustrated. So that traces all the way back to this situation here, though, in the sense that if we take too long to actually process these requests, we endanger hitting that deadline, because we don't actually have that whole 2.4 second budget here. That's the budget including the entire front end loading. That's the budget including internal processing of these requests. Realistically, a well-performing Drupal site should be responding to dynamic requests to the main PHP portion of the HTML page, usually in under like a half second to a second. Because if you go much longer than that, it's very, very hard to hit the actual deadline at the edge and in users' browsers of the site loading in 2.4 seconds, especially after your marketing department gets to it. So like in a lot of ways, we're trying to earn back the budget on a lot of this stuff, or at least not profligately spend it on like this stuff. So we actually have to have these containers start pretty efficiently. And in fact, like realistically, if you actually take the Cloud Run billing model to this that we're looking at, they round up on the 100 millisecond barrier because it's all billed in 100 millisecond units. So there's a little bit of extra yellow here that is not necessary, but you'll notice that we haven't actually flooded this thing with yellow infrastructure, nor have we allocated particularly excessive infrastructure. We do pay a lot more for this yellow than in the previous cases, usually about 2.5 to 5 times as much for the same resources as in this kind of model or this kind of model. But it actually works out, because when you can actually shape that infrastructure at 100 millisecond boundaries and you can fire it up dynamically, Google Cloud Run is able to start a container and hand off execution to us in about 400 milliseconds. So we're able to actually start these containers pretty dynamically. But we wanted to actually look at the cost regarding like our actual traffic on the platform. So I've used actual traffic data from Pantheon for a week of traffic in early December to model like how does this actually affect infrastructure cost? Which is not the easiest thing to do, because like these containers can handle up to some number of requests concurrently. They have these, everything is billed in 100 millisecond units of time. So if you take 10 milliseconds, you actually need to account for 100 in the model. If it takes 101 milliseconds, you need to account for 200 milliseconds in the model. So this is showing the initial way that I was modeling this using Pandas in Python, which is an open source data analysis framework. I actually had to drop that and switch to using BigQuery to do the analysis in December, because running it in Pandas was going to take like a month, like to process a week of traffic. At least on my laptop it was. And I didn't put a lot of effort into trying to scale up the Pandas implementation. But this is how I did it in Pandas, which is I took our edge logs, which contain all of our traffic. I filtered out everything that's hitting the cache at the edge. I filtered out all the things that are not actually going to PHP. Actually, no, I did not filter those out, because those do need to reach the containers. I filtered out everything that hits the cache at the edge. And all of our data for our edge logs is all the start time of a request and the duration of it. So I had to convert that over to start and end date times. And then what I did is I aligned those with 100 millisecond windows, where basically I took every second of the day, broke it into 10 sections of 100 milliseconds, and bracketed a request. So if the beginning of a request falls in the 100 millisecond window, I rounded it to the bottom of that window. And if it falls, and wherever the end of the request falls, I rounded it up to the next 100 milliseconds. So this actually can round up a lot, and perhaps more than even Google really bills. Because if you had a 50 millisecond request that straddles those two things, I'm counting it in this model as 200 milliseconds. Explode was my favorite part of this whole thing, actually, because what it basically did is allow me to break a request that spanned an arbitrary number of 100 millisecond blocks into a request that essentially was built out of individual 100 millisecond requests that are serial, like that are just that have no overlap, but never exceed 100 milliseconds. So essentially, by this point over here, I have a ridiculous number of 100 millisecond requests that are all perfectly aligned and are all exactly 100 milliseconds. But I can't use the same processing for all sites on Pantheon. Every site on Pantheon has its own code base. In fact, every environment on Pantheon has its own code base. Like a given site could have multiple ones. So I can't share those. So grouping by service pool basically meant to break it out into the individual runtimes in a serverless world that they would be on. And then I divided it, rounding up with like a ceiling on the actual concurrency. Because if you have, if the containers can handle up to 4 requests at once, and that's what their allocations are set up for, even if I have 2 requests, I have to fire up a container that can handle 4. So this handles most of the concerns of like mapping traffic over. And it came down to about a third less than our current cost, which was kind of interesting because like I said, these resources individually are much more expensive than we spend today. But the difference is that we run our infrastructure and capacity planning on almost a monthly or quarterly basis. So when we have infrastructure deployed to North America, we kind of add more virtual machines to it as they're needed, but we don't scale that over the day or the week. We don't have a process that is quite that responsive to resource changes. But that actually maps really poorly to our traffic, because like most of the visitors to these sites are humans, and humans are diurnal. We're like awake during the day and we're asleep at night. And our infrastructure is often deployed to the regions that people are accessing the stuff. So there's very little access to the North American region of Pantheon in the middle of the night in the US. Likewise, there's very little access to the Australian region of Pantheon in the middle of the night in Australia. We don't currently adapt to this. There's also a pattern that humans have of access to these things over a week. I don't know a word for that. But if there's an equivalent of diurnal patterns for weekly stuff, we see that too. Our peak traffic day is almost invariably Wednesdays. And our lowest traffic days are usually Saturdays or Sundays, because most of the infrastructure that we deploy and most of our customers are dealing with business needs, business to business or workday related things, or just how people handle the professional aspects of their lives more than, like, we don't run a ton of entertainment magazines, for example. We have a few. So even if we're paying massively more per unit of resources, if we can constrain the allocation of those resources down to this like surgically cut, like with a scalpel set of things as necessary, we actually come out way freaking cheaper. And this is before doing anything particularly clever about the allocation of requests. Like, this doesn't even include the modeling of what I was showing earlier with the multiple Tetris boards where like you send the simple requests to one thing and the complex requests to another thing. So, trade-offs. I mentioned the idea, like the trade-off of these resources are super expensive. We need to have them start cold in order to start from zero, like to scale down to zero if we want to maintain sensible costs on this. But I haven't talked about all the other systems that we're running, like our file system and how we run databases. And this also has its own interesting trade-offs in this like next generation world. The first one, and I think thing that we find most frustrating, is that we're probably going to have to spend a lot more money on databases than we do today. We really want to get better databases out to our infrastructure and customers, probably using Google's Cloud SQL. And there's pretty much no way to fudge the actual allocation of those resources in a way that actually would maintain our current cost on this and have customers have a great time and have a lot of exclusivity of resources. So we have been looking at how to map this stuff out. And like I was mentioning about the bin packing problem of like Tetris pieces dropping, databases almost represent a much more slow-moving Tetris game in a sense of like, it's very hard, or I should say, it's a much harder board to widen than it is for runtimes. So we're going to probably be stretching both up market and down market in some of our approach on this. Like, it's likely that for our very top of the line databases, we will have better ones than we do today by almost every measure in the sense of how they replicate, how they fail over, what their performance is. But we are also looking at needing to do some bin packing on the long tail. Some of our largest customers are universities with sometimes thousands of sites that get fairly low traffic. In order to efficiently manage the databases, we are probably going to have to combine multiple sites from at least the same customer into using the same provisioned Cloud SQL instance. This may also improve performance because it also will provide more resources that are fungible between those sites. They will still have totally separate databases from the perspective of Drupal, in the sense of you're not going to have to play with settings.php and like put prefixes on your database or anything. Like, it's not like that. I just mean that the actual MySQL server would actually be the same one serving multiple sites. And so we haven't finalized this, but we're looking at probably providing unique databases for everything that is above our Pro Starter plans. And then for Pro Starter and basic sites, doing something where it's shared between 5 to 20 sites for a given database. It's one of those kind of trade-off things where like it should improve the reliability of the platform and I hope the performance as well, but there's no like magic thing where we can be like every single environment of every site gets its own database. Nobody can afford to do that. Even if we just didn't make any profit and we charged you for that, it would be much more expensive than what we do today. Things are looking really good though for the file storage stuff. What we have here is I'm showing some benchmarks that we've been doing on our next generation file storage prototypes, where on the on the right-hand side, there's a cluster representing Valhalla. In the middle is a cluster representing local disk, which is not an option for us, but is like there to like give a bench, like give perspective on the relative performance. And then the next generation that we're expecting to do for the file system is shown over here. As the graph graduates from the blue on the left to the orange on the right, it is going from the P50 to the P99 of the actual latency we see for these operations. This particular one, and we have an absolute boatload of these benchmarks, but I just picked out some of the most representative ones. This is the case for concurrency level of 10 reading 1 megabyte files. Concurrency level 10 is reasonably representative of a PHP FPM pool that's accessing the file system. But the takeaway on this is across the board, from the P50 up to the P99, we actually see, we're likely to see some benefits over the current implementation. Although, honestly, if you look at the scale on the side of here, like this is all quite fast. None of this is nearly as slow as even a local spinning Rust disk. Like I remember back when I had systems spinning Rust, and usually the latency of a random seek alone was more than 10 milliseconds, which is off the chart on here.
Cool. Are you going to tell us more about the next generation system?
It's actually largely GCS fused with GCS. Like there's not actually a lot of secret sauce to it. But the findings for this don't necessarily carry over to other clouds because Google Cloud runs the metadata for Google Cloud Storage, which is their S3 equivalent, on top of Cloud Spanner, which is their super distributed database that you can buy out also direct access to for database and storage needs. But it's very low latency accessing it. So what you're seeing here on these reads, this is not really reading the body of the file, actually. What you're really seeing here is something representative of a case where the GCS Fuse client, which has its own local cache, is able to then go to GCS and revalidate its local cache, that is actually the common case for a file read on Pantheon. The vast majority of the communication that our web servers have with the file system servers is revalidating their caches to ensure that the file that they're about to read is actually the current version of it. So that's what you're seeing here, and that's also why the latency is this low. You can't actually transfer a file off GCS this fast, but that's not what you're doing in most cases. You're just checking whether the file has changed. And then we want a really nicely bounded thing here. The latency does spike a bit more when you get to the larger files that are not going to be locally cached, but once you're dealing with 100 meg, 200 meg files, sub 10 millisecond latency is not that important anyway, because like you're typically accessing a really large object or transferring it to a browser that way. Like most people don't have web pages depending on 200 megabyte assets, and if you do, you should probably change that. I considered 1 megabyte to be like a nice middle ground because we tested all these different sizes, but almost all of your aggregated JavaScript, all your aggregated CSS, many of your images are going to be a megabyte or some small multiple of that. I didn't want to go with the trivial tiny file sizes, and I didn't want to go with the 256 like megabyte ones or gig ones for this thing here. We have the benchmarks for it. In fact, the new system wins a lot more as you go up in file size. So in some ways, I'm not even showing all the biggest gains. And then we have file writes. This is kind of fake. Because when you write to a local file system, the kernel is able to confirm the write without having fully flushed and synced it. Whereas if you're dealing with a distributed file system over a network, you cannot flush or close a file handle without actually finishing the write to the file over the network. So a better thing would maybe be comparing against something off the shelf like NFS, but that's not a thing that's under consideration for this. So we mostly compared today versus like local disk for curiosity versus the next generation, which is GCS fused with Google Cloud Storage. As you can see here, very different scale on the left, but generally you shouldn't be needing to write tons of files on a given web request, especially in the middle of an interactive one. So you have a little bit more of a budget here. Like if you're looking at these file reads, Drupal sometimes reads 100 files, looking to make sure that the image cache has been, actually it doesn't check the image cache ones, those are dynamically created, but it does check whether all the aggregated JS and CSS and other and Twig templates are all present for the given web page that's being loaded. And so this is sometimes accessed hundreds of times over a request. This is not. This is like something that Drupal does when a Twig template needs to get updated or a CSS or JS aggregate doesn't exist yet. So you typically have at most a handful of these in a request. But we're beating all of the current benchmarks. So if you're getting adequate performance today, you will continue to get that performance or better as we look at moving more directly to these native cloud resources. It didn't used to be like this. Like it used to be that like writing and reading things on S3 and S3 equivalents like took seconds. So that's why we built Valhalla, but like it isn't as important anymore. There's also a really cool cache that Google has, and I think it's going to GA or some sort of early access this quarter, allows inserting an SSD-backed cache between the application and Google Cloud Storage. And we are also investigating that. We have the benchmarks from the setup on it, but I left them out because it wasn't actually benchmarked properly on this. Like we were testing it in a way where it was like these were all run on a single container against cloud storage, and you really only see the benefits of what Google calls anywhere cache once you have multiple containers accessing that same bucket. But it's a friggin' cool design of a cache because like they keep all of the coherence managed through the Cloud Spanner metadata system, so you can introduce this cache and it doesn't introduce any incoherence in the actual experience of using the file system. It can only accelerate it. We're also looking at where our jobs run. Josh Koenig likes to like call it a pile of Jenkinses, like the way that we like historically run this stuff. We run about 7.4 million jobs every day between like cron, backups, workflows, and other things. And we've ported like a third of those over to cloud native stuff with Cloud Build. Some of it, like this is in the trade-off section, so I'll tell you what the trade-off is. Like we transferring a full container image to a worker like Cloud Build sometimes takes up to a minute or two to start some of these jobs, and we're looking at like our options around these things. So our jobs, as we move them, are getting more reliable and more scalable, but we're also running into some new performance headaches with them that are biting some customers because it turns out that moving from something that is like fast but brittle to something that is like slower but robust has trade-offs. So like, but it's also easier to optimize something that is slow and robust into something that is fast and robust than it is to evolve something that is brittle into something that is robust. So we're working on this, and we do ask that you kind of bear with us on some of cases where like the initial like speed of doing a push and getting it out to a deployment has some regressions right now. So I actually really don't have a lot of time for questions, but I'm happy to take any ones that people have.
So are you locked in on Google? With these
No, not really.
Okay.
I'll tell you the same thing that I tell engineers internally who have asked me this exact question. So when you're negotiating cloud contracts, the important thing to have is what negotiators call a credible threat. A credible threat is the idea that you need to have say, fungibility of your deployment over to another cloud or other infrastructure, so that the other side of the negotiating table, in the case of Google versus Pantheon, does not believe that they will just hold on to your business regardless. So this it also has a bit of a Pareto aspect to it in the sense of like the 80-20 rule, where about 80% of our cloud lock-in is on our control plane, which is not the majority of our spend, and about 80% plus of our spend is for the customer resources, which is also the kind of lighter weight integrations with the cloud, in the sense that we have far more services that we run for our own purposes than pieces we run as parts of a stack for customers. Where I'm getting with this is that we don't actually have to have portability of our entire stack from our control plane down to customer resources in order to actually have a credible negotiating position on this. What we need is the ability to deploy customer resources to the cloud of our choice. Now, the resources that are getting deployed to cloud native here are being deployed through, depending on whether you want to look at it as like Terraform or OpenTofu. Like OpenTofu is the fork of Terraform that I think is part of CNCF now, as the like fully open source thing. It's basically Terraform, but like not closed. But these are able to characterize resources in a fairly portable way across clouds, in the sense that we can define a GCS bucket for something deploying to Google Cloud, and we can define an S3 bucket for something deploying to AWS.
Sure.
So the goal we have around this, or the goal I have really, is that we can set up a defined cloud deployment that is able to target Azure or AWS with cloud native infrastructure there, and that way be able to maintain a sense of cloud portability. And not necessarily for our entire stack, including the control plane, but it basically to be able to provide a compelling perspective into how we actually do have the ability to move around 80+% of our spend.
Sure.
Which at that point, that is a credible threat.
So do you actually do the exercise of deploying infrastructure on other clouds?
We haven't yet. But the
And I
deployment...
guess I was curious because you were talking about the speed advantages of the Google Cloud Storage, maybe more than S3. And would you have like a giant regression if you deployed that on S3?
Not necessarily. We would just make different choices.
Yeah.
There are two different paths that we could go on S3 for it. And I don't love them as much as the path on GCS, but like they will totally work. Mm-hmm. One of them is S3 low latency. Mm-hmm. So there is a low latency version of S3 now. You pay quite a premium for it for the object storage. Mm-hmm. And it's single zone in the sense that we would need to ensure that we have a durability strategy for it between backups and other things that doesn't just rely on the S3 durability. But it's super low latency, and if you mount that into containers, it will perform at least as well as this stuff. In fact, the writes will outperform this because the writes do not go back to a slow, durable store the same way that they do on GCS. The other approach we could be taking, and this is the one that Acquia took, as far as I know, for their Cloud Next product infrastructure, is that they're using the NFS file service on AWS, right, which is where you can allocate a volume for file storage, and then you can mount it using NFS.
Yeah, that's what we're doing. We're migrating AWS and using that, yeah.
Mm-hmm. Things are generally moving away from Gluster these days. Mm-hmm. Even Red Hat is moving away from Gluster. I don't think they're supporting it in the next Red Hat Enterprise Linux. Mm-hmm. We could also use that on AWS. You might take that statement and throw it back at me from the perspective of like, well, David, why don't you use file store on GCP? Because Google has an NFS service. The issue with Google's NFS service is not that it doesn't perform well. The minimum volume allocation you do is so high, and actually they spin up like some VMs in the background to run it. So it has a really high cost associated with it, even though it's a decent product. Yeah. Whereas the AWS NFS thing, you can get it in tiny chunks. Databases on AWS also more flexible for serverless. The weakest spot on AWS, I would say, is the equivalent that they have to run Cloud versus Cloud Run, because Lambda for containers does not have nearly as efficient of a resource allocation model, and Fargate is kind of like not the best thing to use these days. So the answer is not that we would necessarily struggle, it's that the strengths of these different clouds are different.
Sure.
And we would need to take that into consideration for it to be reasonable, but I have every reason to believe that like we could do a great footprint on AWS or Azure if we wanted to.
Right.
We would just have to think through it. And I do kind of want to do it because like it's fun. Like I didn't get into like the whole tenant model that we're working on these days, but like a lot of our tenant model is about like fire up a project or a space, grant a run of Terraform admin access over that specific stamp of infrastructure, and then let Terraform run given the parameters that are derived from the customer's configuration. But that we're targeting that right now at a GCP project, but there's no reason that Terraform couldn't just target AWS or Azure and be like stamp out this infrastructure for the site there.
Right.
So like it's a more complex story to tell than like we run everything on Kube and we can just install Kube in all the clouds and run things there. Like
right.
That's how Platform SH does it.
Right.
But the at the same time, the upside to what we're doing is we can take advantage of the unique benefits of these individual clouds. Whereas if
Right.
you're deploying virtual machines and basic stuff to all of them, you basically get the only the common denominator of all the clouds
Right.
at that point.
Yeah.
So, like,
Yeah.
it's a tough question, but like I think we have some interesting answers to it.
Right. Thanks.
Thanks.